Hey everyone, in this video we're going to talk about linear functions and also begin by giving you a brief overview of functions in general. So at this point we've seen a lot of equations in two variables like 2x minus y equals 4 or x squared minus 2x plus y equals 3 minus 2x. Each one of these I can exactly and explicitly solve for y because each equation is linear with respect to the variable y. So it's easy to solve for y just by our linear techniques such as adding or dividing things from both sides. When I solve for y in this context, I can describe x as the independent variable and y as the dependent variable, because the value of y now depends on whatever I choose for x. So, for our first definition, a function is a rule that assigns a set of inputs to a set of outputs such that each input is assigned to a unique output. Now that second part of the statement can be a little bit weird, but I want you to think of it like this way. Imagine that you are sending a person to a place on campus. You can send multiple people to the same building or the same classroom, that's not a problem, but I can't send one person to two places at once. And that's really the rule that a function is observing, is that if I take an input, I can only send it one place. Another way to think of it is with a vending machine. If I type in the code A1, that should correspond to exactly one slot. And it would be a pretty bad vending machine if A1 corresponded to two separate slots, but I didn't know which. Now, that doesn't mean that I can't have two food items or two drinks in different slots. Maybe Coke is popular, so you have multiple slots for that. That still obeys the rule of a function. I can have two separate inputs go to the same output. I just can't have one input go to two separate outputs. Let's draw an example. Imagine that I have a set of inputs being this set of 5 shapes. We'll call this the domain. And then our possible outputs will be the numbers 0 through 4. We'll call this the codomain. And f is going to be the function that assigns a shape to a number. Now the rule that I'm going to give for f is going to be totally random. I'm just pretty much randomly assigning shapes to numbers as long as I obey the rule of a function. So to get us started, we'll do the following assignments. Via f, the circle is going to get sent to the number 0, the triangle to 3, the square to 4, the pentagon to 1, and the star to 0. So it looks like this satisfies our definition for a function. Everything in the domain has an assignment based on f, and even though the assignments here are random for the sake of this example, this still obeys the rules of a function. Each object goes to exactly one output. But what is f evaluated at this crescent shape? We would call that undefined because the crescent shape isn't in our set of inputs, nor is it given an assignment on the right. So we just call it undefined, and this happens a lot with functions. But also notice that circle and star are both getting sent to 0. Again, this is not an issue. This is allowed by the definition of a function. I can send two objects to the same place. I just can't send one object to two separate places. The most common representation for a function is the notation f evaluated at x, which is going to be set equal to some expression in the variable x. For example, let f of x be 3x squared minus 2x plus 1, and let g of x be 3x plus 1 divided by x squared minus 1. We want to talk about function evaluation, which simply just means I am plugging numbers or other expressions into functions, and through the process of simplification, seeing what we get. First, we'll evaluate f at 0. That means that everywhere I see the letter x, I plug in the value 0 and simplify, and this simply becomes an order of operations problem. So f evaluated at 0 is going to simplify to 1. Similarly, f evaluated at negative 2, being careful with our negatives, is going to simplify to positive 17. A common exercise in Calculus 1 will be to evaluate functions at expressions like x plus h. When I plug this into g of x, I get 3 times x plus h, quantity plus 1, divided by x plus h, quantity squared, minus 1. Now this expression only simplifies so far. We get the following quantity, but this is really just getting us used to the idea that I can plug numbers and algebraic expressions in for functions. One very common rule with dealing with functions is the vertical line test. What this means is the following. If I'm looking at the graph of a potential function, if I can draw a vertical line that intersects this graph at more than one place, then I fail to be a function. However, if I can draw any vertical line I want and intersect my function at most one place, then we're good. We're going to talk about polynomial functions a lot in chapter 5, but this is a graph of a polynomial function. You can see that through several vertical lines, I only intersect my graph at one place, so I have no issue. This is a function. However, if I have pictures like circles or graphs that kind of bend in on themselves, these are not functions, because vertical lines drawn show that I'm intersecting my graph at several spots. Now let's talk about linear functions. We just finished our discussion about linear equations in two variables, and we talked about slope and y-intercept, and thankfully linear functions pretty much follow all the same rules, so there's not going to be too much new material in regards to this particular topic. I can express a linear function as f of x equals mx plus b, where m still represents the slope of that function, and b represents the y-intercept. So real quick, let's look at two linear functions. F of x equals to 2/3 x minus 1, and g of x equals to negative 1 over 5 x plus 2. We know these are linear functions because they satisfy the same conditions of a linear equation. Rather, they satisfy the same kind of form. X is taken to a power of 1, and you have the addition of a constant. And thankfully, graphing linear functions is exactly like graphing linear equations in two variables. We have our slope, we have our y-intercept, so plotting those is exactly like what we saw in Chapter 2. So we can see the function plots for f of x and g of x using the exact same techniques. Next, we're going to talk about roots. By definition, a root of a function is a value that I plug into my function and get 0 as a result. Another way of thinking about this is that this is simply just an x-intercept, or it is the x-coordinate of the x-intercept. So whenever I want to find the root of a function, all I do is set that function equal to 0 and solve for x. So if I want to find the root or the x-intercept of f of x, I set f of x equals to 0. This means solving the equation 2/3 x minus 1 equals to 0, which gives me a solution of x equals to 3 divided by 2. Again, we already know that the y-intercept of this function is given because we have the function written in standard form. But finding the x-intercept for a linear function is really not too bad. It's simply just going to be about solving a linear equation in one variable. Now I can do the same thing for g of x. If I want to find the root of g of x, I set it equal to 0 and solve for x. By doing so, we'll see that I get the solution of x equals to 10. Now the way that I've drawn my graph doesn't allow me to plot that point, so we'll just kind of draw an arrow and say it's going to be out in this direction. But I now have the x value of the coordinate of the x-intercept of g of x. We'll talk a lot more about the concept of roots when we get to polynomial functions in Chapter 5. Thank you so much for watching, and join us in our next video for this section about linear regression. This is going to be about applying the concept of linear functions to statistics and to some real-life situations.